So we had our function. So say we had y was equal to, we had a, the function of b x minus h plus k, right? This is our skeleton model. It depends what the actual function is we're dealing with. This function, they are dealing with a square root function. So it's a sideways parabola, right? And the difference here is that normally a square root function is written as y is equal to the root of x.
Yeah.
They've written it as the x is being affected. So f stands for the function itself. So the function itself in this one is a square root. In many of the other ones, say we had y is equal to x squared. Well, the function in this one is the squared, right? So because the function is a square root, essentially I can replace almost the f with the squared, per se. So essentially in their question, let's write it out, y was equal to the root of 2x minus 6. So what they're saying is, because the f represents, what the f is saying is all of this is inside the function. This is outside the function, and this is added to the function. So since these are under the square root, that means they're in the function. So in other words, they're looking for the h and the b. Okay, so this is our horizontal stretch by factor of 2, and this is our movement to the left. Now, this is actually a compression by a factor of 2, because remember it's reversed when it's beat. Yeah. So for the third example here, what they've done is, imagine this. This is talking about a normal function, so we're used to seeing it as either, and in this case we would have, they've actually have two functions here put together. That would be one of our functions, and our second function would be 2x plus 3. Okay? So here's the idea. We have our two functions. What they've decided to do graphically is they've come to a point where this is going to stop, so it's going to go from one function to another. Okay? So here's our function with a graph. Let's draw these as if they were the normal functions themselves to start with. Okay? So the normal function here, f at x is equal to x squared. We know how to draw that. I know that starts at the origin, over 1, up 1. I know it's a parabola, correct?
Yeah.
So 2 is 4, and 3 is 9. 4, 9. So here is our function. Okay? So we have our function here. And the other function they've given us is 2x plus 3. I'm not sure if you remember this, but that's way back when. That's our y equals mx plus b, so it's a linear function. Okay? So if we look here, the slope is 2 over 1, and the y-intercept is 3. So we'll do that one in blue, let's say. So our y-intercept is 2, and our slope is up 2 over 1. Up 2 over 1. Up 2 over 1. And we'll do that with a line. So this function is here. Okay? So right now we have two different functions on the graph. But what this is telling us is this is going to be one function. We're not going to have two graphical representations, specifically because this can't be a function, because if you look at our vertical line test, we're not passing right now, right? It's not making any sense. So this doesn't work. So what they've done is they've given us a cutoff point. The cutoff point is precisely 2. Okay? So before 2, it's saying that it's this function. So what they mean is up to this point, let's get that dotted line. Up to the point of 2, so the left side of this, we're only going to be using the parabola function. So essentially, I can erase this. This part of this function doesn't exist anymore. Okay? And then what they're saying is equal to and after 2, so at this exact point, it becomes a linear function. So it starts up again here. So what it's saying is anything to the left of it, draw that right? Oh, almost. I'll redraw it. Or anything, sorry, to the right of it, at the point of 2, I meant for that to be the side. from the point of 2 is our function. So the key here is, if you notice, this isn't a continuous function. It has a cutoff point, and it becomes a different function after that point. What the other key thing is, though, I want you to notice, it says when it's less than 2. So that means when I get to the point 2, I actually have to represent the 2 with a little hollow circle, essentially saying that I'm not existing at the point of 2. While with the other function, it says it's equal to 2. Yeah. So at 2, this function actually exists. So that's where we have our solid circle. We're saying this function starts at 2. We're saying that this one stops just before 2, whatever number you want it to be. Anything less than 2, we're using a parabola. Anything after 2, we're using a linear function going up. And that's our cutoff point. Okay, so right now we're trying to figure out what this function is, essentially, 3 at x, okay? And we know that this is some form of this function, f at x. I know that is some form of it. And remember, this is our base model, okay? So if that's the form of it, are we subtracting anything or adding anything on the outside? No, so we know we're not dealing with an H or an K. Again, I don't remember what letters your book uses, but so that means we're not shifting it to the right or shifting it up and down or left and right. We're doing some kind of stretch, yeah. And in fact, they're actually going to be the exact same thing, whether I call it a stretch of 3 or a compression of 3. They're going to end up doing the exact same thing to this line, okay? Because here's the idea. Let's say we have a straight line, okay? Let's say this is on a 45-degree angle. If it's A, that means it's a vertical stretch of 3. Yeah. So say this was going up 1 over 1. I now go up 1, 2, 3 over 1. Okay, so let's see. I'm going to draw my line quickly there. This would be a stretch, a horizontal stretch of 3, right? Oh, okay. Yep. Okay, so again, it can sometimes be hard to recognize what function. So the mathematical symbols or equation before the if, that's the function. That's what is going on. So right here, this is technically still a linear function, okay? They've given us actually 2 linear functions. Again, I'm just going to show you why. Y equals mx plus b, right? Well, in this case, I don't have an x. So we assume the slope is 0, okay? Because there's no x in this equation. So I'm assuming slope 0. Well, x is, m is 0. So that means everywhere on x, I'm just going to have a b-intercept. We're talking about the b-intercept of 2. So what that means is, before 1, let's get our line here, for the number 1, so I'll do it in red. So this is x, and this is y. So when x is less than 1, so that's technically right here. I'm going to put a 0 there because it's not equal to 1. When x is less than 1, they've just given us the number 2. So what they're saying is it's always going to be 2. So when x is negative 2, y will be 2. When x is negative 6, y will be 2. When x is negative 10, y will be 2. Okay? The other thing they've done is, again, they've given us a linear function, y equals mx plus b. But this time, they've given us 3x and there's nothing to the side of it. So we can assume technically there's no y-intercept here. Okay? But what they are saying, so what they're saying from here, if there's no y-intercept there, 3x, when it's at 1, we have to figure out it only exists from the actual point of 1 and beyond that. Okay? So we actually have to figure out what 3x is when it is x is 1. So we have to figure out, essentially the function says f at x is equal to 3 at x. 3x. So when x is 1, because that's where we're starting, let's figure out what it is. So we plug that in. When x is 1, what does our function represent? 3. So it starts at y is 3, right? Yeah. And then let's say x is 2, because that would be our next step on the graph. What would it be? 6. Yeah, exactly. So when x is 2, it would be 6. So we're way up here. So now I can continue my function and just kind of draw it out. I get that function. Okay, now I know I did that part in red. Let's call it. Let's do the hoop in black, just to say that to the left of 1, it's a horizontal line. So I knew where to stop because of the restrictions. They said that this graph to the left of the number 1, so that's from here all the way on, x was always equal to 2. Think of this, I know they've written it funny, but see how this is f at x and they got the squiggly? You can almost think of that as an equal sign. And what they've really done, I guess another way to write this is, I'm going to write it down here. Let's say f at x is equal to 2, and f at x is equal to 3x. The only thing is, this one only exists when x is less than 1, and this one only exists when x is greater than or equal to 1. So this is a function, f at x is equal to 2. And remember, we can replace f at x with y equals 2 or y equals 3x. That might be easier in your eyes to graph. Y equals 3x, does that look a little more linear to you?
Yeah.
So we plug in a value for x and we get a y coordinate. Essentially, what we're doing is we're putting in an input, solving the output. So when x is some number, what is y? Well, in this one, no matter what x is, because I can keep plugging x in, my y always equals 2. So that's how I know it's a horizontal line, because it's not changing anything. I could say x is infinity. Doesn't matter, y is 2. That's how I know it is a flat horizontal line.
Oh, okay.
Does that make sense?
Yeah.
Okay. Okay, so the first precision function, sorry, they've given a precision. Piecewise function, f at x has got 2 functions, the absolute value of x plus 2, and that function only exists when we're less than or equal to 1. The other function is a parabola, looks like, that's been transformed a little, and it only exists when x is greater. Oh, sorry, the negative one, both of these? Yeah. Negative 1. So I'm just going to do, I'm going to get the 2 base models of these, okay? Just so it makes sense. So the base model of the first one, f at x, is equal to the absolute value of x. Absolute value of x is literally 2 45-degree angles. You got it. So we got baboon and baboon. Okay? Now, according to our function rules, this is an h as we call it, and it's plus 2, so that means from the origin, we've moved 1, 2 to the left. So my new function should be this to 45 degrees and this to 45 degrees. And just to make sure that's right, I'll actually plug in values for this, okay? Quickly. So remember, it was f at x was equal to the absolute value of x plus 2. When we're at, and since this function actually only exists from, put a nice red line, negative 1 we said, right? This is where the function technically is split. So technically, none of this stuff exists here. It's only down here and then up. And we can make sense of that at negative 1. Okay, so let's plug in at negative 1. Sorry, that's supposed to be absolute value, not a comma. So when x is negative 1, so we make our little xy chart. Okay? When x is negative 1, and that's where we start, we plug it in. Y is 1. Right?
Yeah.
When x is negative 2, y is 0. When x is negative 3, y is what? Do you know? Close. The only thing we're missing, you do have it, right? Oops, that's a straight line. Plus 2.
Oh, yeah. Oh, my gosh.
Because it's absolute value.
So it's 1.
1. Right? And then from so on, we're going to go up, and it's going to be 2. So let's plot those. These are literally coordinates. Negative 1, 1. Negative 2, 0. Negative 3, 1. Negative 4, and 2. Okay? So since those are coordinates, this is our negative 1. That 1. Negative 2 was 0. Negative 3 was 1, 2, 3, 4. So now we have, and I'll get rid of all this other junk so it makes sense to us. Delete. Okay. we can get rid of all this other stuff here. Because the function we're really trying to draw now is right here.
Mm-hmm.
This is it. This is the whole function up to 1. Okay? So now we've drawn the function. Actually, I'll do it in solid just so it makes sense. Remember that we figured out this and we figured out that.
Mm-hmm.
So that's the function to the left of 1 because that's our cutoff. And I'm going to put a dotted line there. It's always good to know where the cutoff is. I'm putting that dotted line there just because I know that our cutoff is at -1. So something's going to change here. We go from function 1 to function 2. Function 2 is an upside down parabola.
Yeah.
That's been what from the origin?
Move up 2.
Yeah, the vertex has been moved up 2. So I can literally start drawing my original 1. I go up 2. It fixed it.
Mm-hmm.
And then we just go down 1 over 1, down 1 over 1. Hey, it looks like it connects perfect there. 1, 2, 3, 4. So and it goes down like this.